Well, we've got another statistical topic for you tonight called margin of error. So in statistics, we attempt to infer characteristics about a population from a sample statistic. Because remember, it's pretty difficult to get the whole population, so we create these samples instead, and then we infer something about the population. These inferences usually have a degree of uncertainty, so that's kind of the key for tonight, this uncertainty, which we call the margin of error. So here it is, the margin of error. This measures how accurate we believe our sample statistic to be relative to the population. Okay, and this is key. We want to get this definition down. How accurate we believe our sample statistic can be relative to the population. So let's recall that the normal distribution of sample means has a 95% of the sample mean within 2 standard deviations of the population mean. So remember, there's 3 numbers you have to have memorized. That's 68, 95, 99. 68 falls within the -1 to 1, so 1 standard deviation of the mean. Remember, the mean's in the middle. 2 represents 95%, so all that added together makes 95%. And then 3, of course, is 99. But our goal is really to focus on 95% of the data, which is 2 standard deviations. So here's the key. The margin of error can be found by multiplying the standard deviation of the distribution of the sample means by 2. I apologize for that notation there. Of the distribution of the sample means by 2. So let's go ahead and put it in our notebook. It's really 2 times the standard deviation. This gets me, I'm going to call it MOE for margin of error. Okay, so let's revisit a sampling distribution of some sample proportions that we've talked about in previous days. A computer simulation was conducted with a sample size of 80 coin flips. A total of 40 samples were taken. The resulting proportions of heads are shown in the dot plot to the right. For the sampling distribution, the mean is 0.508 and the standard deviation is 0.061. So we've talked about this before. Remember, our mean should kind of be in the center of this distribution. So does it make sense that 0.508 right about here is kind of the tipping point? Half the data should be on the left, half the data should be on the right. Our mean should be in the middle. So A, is a sample proportion of 0.55 a likely result? Well, it looks like if my mean is someplace around here, 0.55 is pretty darn close to that. So I would say yes. Part B, is a sample proportion of 0.38 a likely result? Well, again, I think it's going to be helpful if we kind of draw on where we think that mean is someplace around here. Does 0.38 look like it's close to the mean? I would say that's way on the end, and I'm going to say no, that does not look like a likely result. It is not close to the mean. So here's our next key. The range of values that are likely results are known as a confidence interval. So if we want to estimate the confidence interval that contains approximately 95% of the scores in the dot plot, since there are 40 samples in the sampling distribution, this interval would include all the DES except for the highest and the lowest. So notice it's saying estimate it. So I'm going to guess, it says everything but the highest and the lowest. I'm going to guess someplace from like 0.4 to 0.62. And again, this is just an estimate. This is what I'm guessing it to be. Maybe from 0.4 to 0.62, I'm thinking 95% of the data is going to fall. Not all of it, but 95% of it. And again, this is an estimate. Part D says now find the margin of error. So if you look back in your notes there, we just said to find the margin of error, it's a simple formula. We're going to use 2 times the standard deviation. Now, they told us they're going to tell you the standard deviation, or it's something you can easily calculate. So if I look back up here, the standard deviation is 0.061. So the margin of error is 2 times 0.061. So I'm saying my margin of error is 0.122. Okay, suppose that 50 random samples, each of size 10, produce sample means displayed in the following dot plot. Okay, so I want you to estimate what you think the mean is. Would you think the mean is perhaps 5.2? Do you think the mean, that's where the data is centered around? Well, I hope not. I hope you're thinking it's someplace over here, where half the data is on this side, half the data is on this side. Maybe, I don't know, a 7.2-ish number? Okay, so your goal is just to estimate what you think that mean is. So now that we estimated it, let me tell you, the actual mean is 7.5. And the standard deviation is 1.75. So if I wanted to calculate the margin of error, all I have to say to myself is it's 2 times the standard deviation. So 2 times 1.75. So my margin of error, I would say, is 3.5. So what does that mean again? Why is this margin of error so important? Well, remember, 95% of the data is where my margin of error is going to fall. So I can say I am confident, hence the words confidence interval, that 95% of these means will fall between so 95 means plus and minus 2 standard deviations from the mean. So I'm going to take my 7.5 and I'm going to add my 2 standard deviations or my margin of error, so plus 3.5. And I'm going to take my 7.5 and I'm going to subtract my 3.5. Let's see, I get 11 here and I get a 4 here. So I am 95% confident that all of these numbers, all my means, not all, 95% of them should fall between 4 and 11. So let's go ahead and look at that graph that we had. I am 95% confident of this interval from 4 to 11. So most of my means should fall in between that range. That is my margin of error. Anybody in here is a good number to have. Now, the closer I am to the mean, the better, but anybody in this confidence interval, we can feel comfortable saying we're sure about. As of December 30th, 2015, the New York Knicks record was 15-18. So that's 15 wins to 18 losses if you're not sure how to read that. What proportion of the games have the Knicks won at this point in the season to the nearest hundredth? Well, they have won 15 out of how many? I would say 33 total. So to the nearest hundredth, I would say their winning percentage is 0.45. Before the season started, your friend who is a Knicks fan stated that the Knicks have a 65% chance of winning each of their games this season. To test that theory against the Knicks' current record, you run a simulation based on the assumption that the Knicks have a 65% chance of winning games. Each dot in the plot below represents the portion of games the Knicks would win. Each has a sample size of 33, simulated 100 times. So there's 100 dots here. I simulated it 100 times, and each of my sample size for each simulation was 33. So B says, estimate the mean of the sample distribution to the nearest hundredth. So where do you think the mean is on this dot plot here? Remember, whatever you pick, half of the data should be to the left, half should be to the right. It's kind of like this tipping point. So again, if I just have to ballpark it and guess it, I'm going to say someplace right around here. I would have half the data to the left, half the data to the right. So maybe I'm estimating the mean to be 0.65. Now it says estimated confidence interval that is approximately 95% of the sample portions to the nearest hundredth. Okay, so again, this is just an estimate because we don't have the actual mean or the actual standard deviation. So I'm saying 95% of my data should fall in here, not all of it. So I'm probably not going to go from here to here. I want 95%. So again, this is just my ballpark estimate. I'm going to say maybe from 0.45 to 0.85. I am confident, hence a confidence interval, that 95% falls within those two. So based on the estimated mean and confidence interval, what is the estimated margin of error? Okay, so I'm going to kind of work backwards. I know the mean plus 2 standard deviations, I said I estimated to be 85. And I estimated my, or 0.85. I estimated my mean to be 0.65 plus 2 standard deviations to equal 0.85. So I would say, 2 standard deviations is approximately 0.20 if I subtract that over. And again, the margin of error is 2 times the standard deviation. So I am estimating that my margin of error is 0.2. Okay, so let me say that one more time. I said the mean plus 2 standard deviations, that's the margin of error, is 0.85. My mean was 0.65. I subtracted that over, so I said 2 standard deviations is 0.2. Therefore, I'm estimating the margin of error to be 0.2. So here's our data. The actual mean proportion for the simulation is 0.658. And the standard deviation is actually 0.093. Use this information to create and determine a 95% confidence interval for the simulation. All right, so I first want to get my margin of error. My margin of error is 2 times the standard deviation, so that's going to be 2 times 0.093. So I'm getting a margin of error of 0.186. Okay, so was I pretty close to what I estimated it to be? I would say so. Now it says we want a confidence interval of 95%. So I'm going to take that mean. I'm running out of room here. I'm going to slide over to the left. I'm going to take my mean of 0.658, and I'm going to add my 2 standard deviations, or my margin of error, 0.186, and I'm going to subtract it to get a nice confidence interval. And let's see, I got 0.844 and 0.472. So I am 95% confident that these should fall between 0.42 and 0.844. So that is my confidence interval, my range of numbers that are acceptable. So now the question says, using your answer to this previous part and the confidence interval that you just found, does the Knicks' current record support the claim that they have a chance of a 65% chance of winning their games each season? Well, as long as this number falls within your confidence interval, we can say, yes, that supports our claim. So does 65% fall within our confidence interval? I would say yes. So we can support that claim that we think they have a 65% chance of winning each of their games this season. Okay, so that margin of error is just an interval where as long as our data falls any place on that interval, we are confident in saying that this can happen. If it falls outside, then we are not confident in that answer. So because we don't want to seem overly argumentative, you propose to your friend that the Knicks could have a 55% chance of winning each game this season and provide the following simulation data to support your claim with a proportion of 0.55 and a sample size of 33 simulated 100 times. So again, there should be 100 dots here. We simulated this 100 times. Our sample for each run was 33. And we're saying we have a proportion of 0.55. So again, I'm estimating my mean to be in the middle of the data, so to be 0.55. So in the following 2 ways, explain to your friend why the simulated dot plot supports your claim even though the sample proportion of 0.45 from the beginning of the season is still in the left tail of the dot plot. So my informal way is to say, okay, if I think the mean is 0.55, I am going to be 95% confident. I have a margin of error, so I'm going to be 95% confident that most of the data falls between here and here. So my 0.45 claim is still in this margin of error. Now, formally, let's go ahead and actually find the margin of error in our confidence interval. So if the standard deviation is 0.094, my margin of error is 2 times that standard deviation. So I've got a margin of error of 0.188. Okay? So that means I can go 0.188 in either direction from my mean. And my actual mean is 0.554. So I'm going to go 0.554 plus my 2 standard deviations, which really is my margin of error, and 0.554 minus my 2 standard deviations, which again is that margin of error. So I am 95% confident that as long as my prediction falls between 366 and 0.742, and again, we were trying to show that even though this 0.45 seems smaller, it does fall within that confidence interval that we just had. So again, as long as we fall in this confidence interval, we can support our claim. All right, a simulation of 500 coin flips was repeated 1,000 times. The proportion of heads in each sample is recorded. So again, this represents the number of heads gotten when I flipped a coin 500 times, and I did this 1,000 times. So how many dots are there in this dot plot? Well, I repeated this process 1,000 times, so I would say there are 1,000 dots in this dot plot. Each dot represents the proportion, okay, or probability that a heads came up. Does this sampling distribution come closer to approximating a normal distribution than samples that we talked about earlier? Well, why do you think this is true? Well, hopefully you're saying this looks roughly mound shape and symmetric. Okay, I wouldn't say this is skewed at all. I'm saying this is roughly mound shape and symmetric. Now, why might it look more round shape and symmetric than some of the other ones? Well, how many times did we run this sample? Okay, we ran it 1,000 times. So the more and more times you run a sample, the more mound shape and symmetric it should get. So I'll let you go ahead and answer that question. Okay, the next one says the mean and the standard deviation of the sampling distribution are 0.560 and 0.021. Use this information to find a 95% confidence interval. Okay, well again, I'm going to go get and express it with a margin of error. Let's go get that margin of error. Remember, a margin of error is just 2 times the standard deviation, so 0.021. So I'm going to say that margin of error is 0.042. Now it wants me to get a 95% confidence interval. So remember, 68, 95, 99, I have to go 2 standard deviations out. So I'm going to say my mean is 0.560, and I have to add the 2 standard deviations or the margin of error, and I have to subtract it. Let's see, so I'm getting a range of 0.518 to 0.062. Okay, so this represents the 95% of data that I feel comfortable saying we can have. Anything outside of that is going to be incorrect here. So it says this confidence interval is much smaller than the ones we found on the previous page, and they're right. This is a very, oh shoot, did I write that number down? I'm sorry. This should have been 0.602. I apologize. My number's backwards. This is a pretty tight confidence interval. And notice how small our standard deviation was. So remember, once your standard deviation gets really small, that means this data should be really close together. So our margin of error should get smaller as well. So do you think this is a fair coin? All right, well, that's a great question. If this were a fair coin, what would the proportion of heads be? If you were to flip a coin, you should see, if you flip it 1,000 times, it really should come back down to a what percentage of getting heads. I would say a 50% are heads and 50% should be tails. That would be the probability of flipping a heads. Does that 50% fall within my margin of error? No. So would we assume that this is a fair coin? Absolutely not. We are more likely to get a number closer to the mean or within this margin of error than to actually get that 50%. So I would say no, this is not a fair coin. All right, I think I got a real cupcake one for you here. This represents the result of flipping a coin 120 times. They nicely give me the mean and the standard deviation. So part A just says identify the margin of error. See how simple? You just have to know that formula. The margin of error is just 2 times the standard deviation. So 2 times 0.046. So I've got a margin of error of 0.092. Okay, interpret the meaning of the margin of error in the context of this problem. So I would find the confidence interval. So again, that's just the mean plus or minus the two standard deviations, so 0.502, plus my two standard deviations, which is my margin of error, and 0.502 minus my two standard deviations. So I've got 0.594 and 0.41. So I am 95% confident saying I should get a result between 0.41 and 0.594. So anything that falls within there, we're pretty confident on saying we can get. Anything that outside, we're not confident. Okay, suppose a random sample of size 10 was taken from 100 computer games based on the difficulty level 1 through 20. These are the results. So this represents the difficulty level of a computer game, 20 being the highest, 1 being probably the easiest. Calculate the mean. Okay, so you're sticking all of these in L1. We're running your one variable stats, and you're only putting in L1. There is no frequency list. Make sure there's not an L2 in there. You just have L1. Okay, just when you thought you knew everything, I'm going to throw a little hiccup at you here. Calculate the mean. So you've got that in there, mean, X bar, bam, easy. So my mean is 7.3. Now, here's the hiccup. Calculate the sample standard deviation. I want you to highlight this word sample. Okay, and you're going to come back to your calculator, and you're going to need to copy this screen down here. This standard deviation symbol that we've used right here is called the population standard deviation. And we've used that for everything we've done so far. This question says calculate the sample standard deviation. Do you see this one with the S? What do you think S stands for? Guess what? It stands for sample. Okay, there are two standard deviations given every time. One represents the population, and that's the one we've only used thus far, and this one represents the sample. So this question is actually asking for the sample standard deviation. So I'm going to say that standard deviation is 6.27. Okay, now, which one are you going to use? You're always going to use population unless you see the word sample. So now in this case, I'm grabbing the sample one instead. Find the margin of error. Well, remember how simple that is? That's 2 times the standard deviation. So I've got a margin of error of 12.54. And now interpret the meaning of the margin of error. Well, remember, the margin of error is 95% confident. So I'm going to take that mean, which was 7.3, and I'm going to add 2 standard deviations, also known as my margin of error, and I'm going to subtract 2 standard deviations, known as my margin of error. See, so I got a 19.84 and a negative 5.24. So since that lower bound is really a 0, I'm going to say I'm confident that anybody that falls between 0 and 19.84, I am confident in. Well, I think I saved the best for last here, and this is probably most relatable to what's going on currently in our country. In a population of 500 potential voters, candidate A led candidate B by a 46 to 39% margin. Could these two candidates actually be tied in the population as a whole? Okay, so we're given a standard deviation of 0.022. So let's start with candidate A. Okay, I first need to calculate their margin of error. So I'm saying 2 times 0.022 gets me 0.044. What can you relate that to? Since these are in percents, I think I could really call that 4.4%. So this candidate has a 4.4% margin of error. So if it currently has a 46%, I'm going to say that's 46 plus 4.4, and obviously 46 minus 4.4. So they have a confidence interval from 41.6 to 50.4. Candidate B, on the other hand, obviously is going to have the same margin of error of 0.044, which is obviously equivalent to 4.4%. However, let's see, they had a 39% margin here. So I'm going to go 39 plus the 4.4 and 39 minus the 4.4. We have a confidence interval of 34.6 to 43.4. So the question was, could these two candidates ever be tied? Okay, well, think about what it means to be tied. If it was tied, that means they actually have the same percentage. So if I look at my confidence interval for candidate A and candidate B, is it possible that they ever have the same percentage? I would say yes. What do you think? I would say if perhaps I chose 42%, does that fall within this confidence interval? And does it fall within this confidence interval? So they actually could be tied at a 42%. How about at a 43%? Again, 43 falls on that interval and on this interval, because this is 43.4, so 43 does fall within here. So I would say yes, they absolutely could be tied. They could overlap between that 42 to 43%. Again, maybe it's 42.6 or whatever, but they could overlap in that range because they both have values in that range and be tied. However, it's more likely, I think, that candidate A is ahead in the population just because its confidence interval is a little wider here. Not saying it's true, but I'm saying it's more likely to happen. But the question was, could they be tied? And they absolutely could, because these percentages fall in both of those confidence intervals. Well, I might have jumped the gun. I've got one more question that we have to tie in here. So here we go. A population proportion, P, is the ratio of the members of the population with a particular characteristic to the total members of the population. So here's the deal. What's important that we haven't covered yet? Well, what if the standard deviation is not given? And this is huge. This showed up in our exam last year where they didn't give you the standard deviation, so that changes the game. You have to have this formula memorized. Again, one of the benefits to Common Core, they don't give you any useful formulas. So we do have to memorize this. So the standard deviation is the square root of P times 1 minus P over N. So again, P right here is our population proportion, and N, just make a little note for yourself, is the sample size. So let's attack our first question. Find the margin of error given a proportion of 0.35 and a sample size of 40. Well, if you know the formula, it's not too bad. I have to first find my standard deviation because I know margin of error is 2 times the standard deviation. So to find that standard deviation, I'm doing P times 1 minus P all over N. So my proportion is 0.35. So 0.35 times 1 minus 1 minus 0.35 all over my sample size of 40. And of course, your calculator is going to do that math for you. You're just going to make sure you type it in correctly with the fraction tool. And I get a value of 0.0754. Now remember, that doesn't answer my question. That is just the standard deviation. So to find that margin of error, I have to do 2 times 0.0754, which gets me 0.1508, or I'm going to say 0.151. So here's the second question that got most of us on our exam last year. I don't think you need to copy all of this down here, but we'll highlight one key feature here. A candidate for political office commissioned a poll. His staff received responses from 900 voters, and 55% of them said they would vote for the candidate. The staff then conducted 1,000 more polls of 900 voters, assuming 55% would vote for their candidate. So they're basically telling me that my proportion is my 55%. So notice, to get that confidence level, or the margin of error, I need to do 2 times that standard deviation. And again, they don't give me the standard deviation. So I have to use that formula we just talked about to get it. So again, standard deviation equals my proportion times 1 minus my proportion over the sample. So in this case, my proportion is 0.55 times 1 minus 0.55 divided by, well, how many simulations did they run? They ran 1,000 of them. So when I run that and take that square root, I get 0.0157, which of course was a choice that everybody fell for because the margin of error, remember, is 2 times my standard deviation. So I have to take that value and multiply it by 2, and I get 0.0314. All right, well, I apologize for this being super long tonight, but we've covered, weeks worth of AP stats in just one night. We'll see you tomorrow. Have a great night.